All right, good morning, everyone. So, one more to talk about. So let's remind ourselves of the two different, well, actually just the one type of inductance that we talked about, which was the self-inductance. Basically, we're going to do a little bit different this morning. So I'm going to do one example of this after we refresh our memories. And then we'll do the review. And then I'll bring up the group assignments. And then if we have any time left, we'll start adding inductors to circuits. If we don't get that far, then we'll just do that on Monday after the exam, since it won't be part of the exam anyways. So remember what self-inductance is the fact that I have a solenoid. And then what happens again is as current starts to flow through here, I now go from, say, a zero current up to a non-zero current. So as this happens, I then create a magnetic flux in each one of these number of coils. So in this case, the number of coils times magnetic flux is then equal to what we call the self-inductance times the current, which means that what happens in here is I get a back current, which is either going in the opposite direction or in the same direction as the current, if it's increasing or decreasing the time, depending on what that's happening with that guy, which then is going to cause the current to take more time to increase or more time to go to zero, again, depending on the different directions, which means that the self-inductance by definition then is equal to the number of loops times the magnetic flux divided by the current. And as we talked about, as this thing is trying to force then currents moving through our system, what happens is we generate a back EMF inside of here, which means there's a potential drop going from A to B, which in this case is equal to negative that self-inductance times the time rate of change of the current. So let's do a quick example of calculating self-inductance. So this says, determine the inductance per unit length of a coaxial cable whose inner conductor has a radius of R1 and an outer conductor has a radius of R2, and assume that the conductors are hollow tubes so that there is no magnetic field within inside of the inner conductor, and the magnetic field inside both thin conductors can be ignored. So basically, we're assuming that they have no distribution to them, so they're just shells in this case. And then it says the conductors carry both currents in opposite directions. So let's kind of draw our scenario here. So all this means is I have two cylindrical conductors. So here's my first one. Outside of this, I then have a second one. And the first one has a radius of R1. And the outside one has a radius of R2. And let's finish drawing here. Good. So this is my coaxial cable. And then basically what I was saying is that the inside portion here has a current running, say, in this direction. And then this outside portion has a current running along it in this direction. So that way, if we used Ampere's law on the outside, so if I drew my DL on the outside, Ampere's law would then tell me that the flux is equal to 0, since no current is enclosed, because I have currents in two different directions, so I have the total current is equal to 0, which means on the exterior, the magnetic field is equal to 0. And we're also told that on the interior of this guy, the magnetic field is also equal to 0, which basically means that the current is only running down the outside of this shaft here and on the outside of this shaft here, okay? Which means that the total magnetic field only exists in this region here, okay? So only in between the two. Now we know the direction of that. So in this case, we put our thumb in the direction then of the current, which is pointing in this direction. Our magnetic field would go around in this direction using right-hand rule number 1. So our magnetic field on the inside is pointing around in this direction, B. And since this is the magnetic field outside of a straight wire, we also know then that the magnetic field of a wire, magnitude-wise anyways, is equal to mu naught I divided by 2 pi r. So this is the magnitude of that magnetic field on the inside, which is then curling around in this particular direction. Which means that what down here, the magnetic field is coming out. And up here, my magnetic field is going in. But this magnetic field is spatially dependent. So as I start moving away from R1, the size of the magnetic field gets smaller. Okay? So good. What we want to know then is, what is the self-inductance? Well, we now know the self-inductance is equal to the number of loops times the magnetic flux divided by the current. Okay. So here we have one loop, right? The current's going to go out through here, turn around, and then go back out through the outside portion, and then back in through the inside, which means there's only one loop in this case. So n is simply equal to 1. Nice and easy. So the only thing we have to do here now is calculate the magnetic flux. So let's look at the magnetic flux. So we know the magnetic flux is equal to the integral of the magnetic field dotted by the differential area. Okay. So what does that mean? So let's go back to our picture. So that means then is our magnetic field is here. So let's look at only this picture. So let's draw an area here. So we want to calculate the area through some sort of loop here. So let's say this is my differential area that I want to look through. Now, in this case, since the area is in this direction, it means dA is either going to point that way or it's going to point this way. Because remember, the area is perpendicular to the area which we draw. So here we're going to go ahead and choose that our dA is into the page to make that dot product simply equal to 1. So in this case, this integral then is going to become simply d times dA. So what is dA? So let's redraw our picture here. So what I have going on here is here's my magnetic field going in. This is then the area that I'm drawing. So this area here is going to have some length L to it, but it's also going to have a thickness to it. And this thickness here is going to be this thickness, which I'm going to call dr. Okay. So basically what I'm doing is, if I go back to the original picture, oops, too far. All I'm going to do is I'm going to cut a little tiny strip across here where the length of the strip is simply equal to L, whatever L is, and then the thickness of this is equal to the differential amount in this direction, but this is the radial direction. So I'm cutting a small strip here of dr. So good. So that's what this picture is representing. So again, the width of this thing is dr, the length of it is then L, which means then that's what? dA is going to be equal to the length, which is L, times the thickness, which is dr. So this is my dA. So good. So this is going to be equal to then the integral of b times L times dr. But again, we know b is mu naught I over 2 pi r. So if I plug that in, this becomes I mu naught divided by 2 pi integral, my L on the outside too, of dr over r. And I'm going to integrate this from the inside to the outside. It was okay? What's the integral of RdR? Well, actually, no. dr over r, there we go, not RdR. dr over r. With the integral of 1 over RdR. Natural log, there we go. So this is then equal to mu naught I L divided by 2 pi natural log of R2 divided by R1. Okay. So this is then our magnetic flux. So now, if you plug that magnetic flux back into our definition here, so again, we're just saying that the inductance is the number of loops, which is 1, times the magnetic flux divided by the current. The only thing that's going to happen here is the current is going to cancel out. So from here, we can then say that the inductance then is equal to the magnetic flux divided by I, which is then equal to mu naught, what is this, L divided by 2 pi natural log of R2 over R1. But what we really wanted to do was find the inductance per unit length, which means I'm just going to divide both sides by L. Okay. So this means that the inductance per unit length then is equal to mu naught divided by 2 pi natural log R2 over R1. I didn't forget any factors, right? No. Is okay? So that's it. So this is our inductance. Now, again, if we look at this guy, just like parallel plate capacitors, where we found that the capacitance was only proportional to the geometry of the capacitor, had nothing to do with the current or with the voltage, or in that case, with the charge of the voltage. This is the same thing. So here, my inductance only depends on geometric factors, i.e. the 2 radii and the length of it. Nothing here depends on the current. Nothing depends on the voltage. It's purely geometrically dependent. So if I change the geometry, just like with a parabolic plate capacitor, I change the inductance. So again, this guy is simply dependent on geometry. So again, change geometry, change the inductance. So it's only geometry dependent. Doesn't depend on anything else. So good, so that's it. I'm gonna leave it here and then let's do a review. So let's talk about the exam. So can you believe we've only done 2 chapters? All that material we did was only 2 chapters. Seemed like we did a lot more than that, but that's fine. So good, so let's talk about chapter 29. So first we did chapter 29. So the first part was just talking about the relationship between magnetic field and the electric field, not really a relationship, but kind of comparing the two of them. So we're going to skip that. And then we talked about the right-hand rule number 1, which we'll skip that as well. We'll talk about that again later. So the first thing we looked at was the force on a current carrying wire. So that's equal to I times L cross B. Now here there are 2 caveats that we have to understand. Caveat number 1 is that the wire is straight. And caveat number 2 is that the magnetic field is constant, meaning spatially constant. If neither one of these is satisfied, or if both are not satisfied, in that case we have to use the general expression, which is equal to the integral of the current dl cross b. So this is the more general case. So again, if we don't have a straight wire or a constant external magnetic field, we have to use this guy instead. Good. From here, that brings us to the force on a charged particle. This was then equal to QV cross B. This is not a charged particle. Nathaniel actually got to solve this last night before my daughter put a jihad on us, so that was great. It was an invasion of my daughter. It was great. Okay, everybody's okay? She was quite the pest last night, but it's fine. Okay. So good. So from here, there are things to know. So again, what this tells me then is that what? The force is always going to be perpendicular to the direction of the velocity, which means this thing is going to move in a uniform circular path, which means that this thing is going to have a period, which is then equal to 2 pi m divided by QB, which is equal to 1 over the frequency, which is called the cyclotron frequency. And we also have that, what? Q times B is equal to M times V divided by the radius, which means the radius then is equal to MV divided by QB. So this is the radius of curvature of this circle at which this thing is going to undergo. So these are some important things to know. From here, we talked about the Lorentz force. So the Lorentz force is the total force acting on a charged particle when it's in the presence of both an electric field and a magnetic field. So this guy is equal to Q times E plus V cross B. So this is the Lorentz force. Good. From here, the most interesting thing we looked at was the velocity selector. So the velocity selector said that if we had an electric field, which is say pointing this direction, we then cross that by a magnetic field, say pointing in this direction. And if a particle moved with exactly this velocity, which was the ratio of the electric field to the magnetic field, then it was going to be undeflected. So this is our velocity selector. What else did we do? So from here, we also talked about the Hall effect. So Hall effect was if I had a strip which had a thickness and a length and a width to it with an external magnetic field perpendicular to this, so that this thing had a current running in this direction. We found here that the Hall EMF was equal to the velocity times the width times the external magnetic field. So this distance here is the width, and the Hall EMF is the potential difference between these two sides. So this is the Hall EMF. From here, we then also looked at putting a loop of wire in an external magnetic field. So here, if I had a loop of wire which has a magnetic moment, say pointing in this direction, and this was placed into some sort of external magnetic field, let's say that guy's pointing this way, so that these two are at an angle of theta relative to each other. What we found here is that this guy's going to experience a torque. So the torque, or the magnetic torque, was equal to the magnetic moment crossed by the external magnetic field, which means the magnitude of that torque is equal to the magnetic moment times the magnetic field times sine of the angle between the two of them, where the magnetic moment itself is equal to the number of loops times the current times the area vector. This also has a potential energy associated with it, where that potential energy is equal to minus the magnetic moment dotted by the external magnetic field. We also looked at some other stuff too, like the aurora borealis. We also looked at mass spectrometers, things like that, but those were all examples of just these things, so I'm not gonna write any of those down. Good, so after we got this far, then we said, okay, great, we know how things act in an external magnetic field, but how do we actually calculate an external magnetic field? So that brought us to the Biot-Savart's law. Again, this was the analog of Coulomb's law, so this one is general no matter what. And what this one said is that the magnetic field is equal to, at point P, mu naught times the current divided by 4 pi times the integral of dl crossed by r hat divided by r squared. So let's just kind of write down what some of these things mean. So let's say here's my wire. I got current running in this direction, I, and let's say this is my point P. And let's say this is my DL. Do DL in green. So DL, again, is a small differential length, which points in the direction of the current at that particular location. R is the distance from DL to the point P, and then R hat is a unit vector which points from DL to P. So just so we know what all these different quantities are. From here, we then said we can also look at, if we have great symmetry, Ampere's law. So Ampere's law is the analog of Gauss's law, which requires perfect symmetry. So here what we said was that the closed loop integral of the magnetic field dotted by the differential length is then equal to mu naught I enclosed, where in general, I enclosed is going to be equal to the integral of the current density integrated over the differential area, where the differential area is equal to 2 pi r times dl. Right? Finally, what we said was that now that we have forces and we know how to calculate external magnetic fields, so now we can actually couple these things together. We can actually find some magnetic fields. So some magnetic fields of interest will be magnetic field of a wire, which again is equal to mu naught I divided by 2 pi r. And the magnetic field of a solenoid, which is mu naught n divided by I, where little n is equal to the number of loops per unit length. So basically what we said is now that we have these magnetic fields and other ones that we can actually find, we can now couple those with the forces that we looked at before, which means that we can have forces between parallel wires. So force between parallel wires. So here what we found was that the magnetic force on 1 by 2, which is equal to the magnitude of the force by 2 on 1, was equal to then mu naught times current I1 times current I2 times the length divided by 2 pi d. Or in vector form, we have F12 is equal to minus F21. So this satisfies Newton's third law, where d is the center-to-center distance between the two of the wires. So these are my two parallel wires. The center-to-center distance between the two is d. Now, most of the time, we've always pretended that the wires have been basically zero extent. So when I said I have one wire here, these guys are separated by a distance of a meter. then that just means this side of this other distance, right? So that's our distance d. So here we also found is that if the currents were in the same direction, that then became a attractive force. And if the currents were in opposite direction, then this manifested itself as a repulsive force. And that's it. We're done with that chapter. So, next chapter. Chapter 30. So chapter 30, we then started talking about induced EMFs. So good. So what's our induced EMF? So the induced EMF then is E is equal to minus the number of loops times the time rate of change of the magnetic flux, where the magnetic flux, as we just talked about, is the integral of B dot dA. So this is my magnetic flux. Now, one thing we did find here was that, if we had a straight rod / wire in a constant B field, so in a B equal to a constant, in this case, we found out that this is an EMF which is given by BLV, which is what's known as motional EMF. So here, all that means is if I had a wire of length L moving in an external magnetic field with velocity V, then this is my induced EMF inside of this wire, or rod, or whatever you want to call it, some conductor. What else do we see? What do I want to talk about? Then there was yesterday. I don't know how much we want to talk about yesterday, but confused the hell out of everybody. So what we actually said is that Faraday's law really says that we're actually inducing an electric field, so that the closed loop integral of the electric field dotted by the differential length is equal to minus the number of loops times the time rate of change of the magnetic field dotted by the differential area. So basically here, this is the actual version of Faraday's law. So again, what this one says is that a time-changing magnetic field induces an electric field. Right? Or again, this electric field is circular, it is non-conservative, but it's still an electric field. From here, we then talked about inductance. So we'll talk about inductance. So for inductance, we said we have self-inductance. Is the only type that we really actually looked at. So inductance. So from here, we found that the number of loops times the magnetic flux is equal to the inductance times the current. And then the back EMF that this thing feels is equal to minus the inductance times the time rate of change of the current. I think that's about everything. I mean, we also did generators, but I'm not going to talk too much about that. Yeah, that's about it. Overall, chapter 30 was pretty short. So good. So let's talk about things. Let's go all the way back. So what type of problems to expect? Good. So basically, one long problem is going to involve pretty much everything under that line. So this is one long problem. So pretty much it'll be force on a charged particle moving in a circle with a radius and all kinds of stuff. This one, expect to have a lot of right-hand rule stuff. If you want, we can go over all the right-hand rules again. But this one's going to involve a lot of different right-hand rule type stuff. So this is one long problem. This one, the one above that, this is going to be part of another long problem. Let's call that long problem 2, which will be mixed with this stuff, right? EMFs. So basically you'll have induced EMFs, which are then creating currents. Those currents are then going to be in an external magnetic field, which means they're going to feel forces, blah, 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 blah. So basically all that motional EMF stuff that we went through. Now this one I will also give you a little hint. And that hint is remember friction. Pull back something old on you guys. Friction. See if you remember friction. Not too bad. Don't hate me, Molly. Okay. So, okay? I'm warning you ahead of time. So, the last long problem is then going to be, let's use gray, Ampere's law. So basically just like the last, or not the last exam, the second exam, which had a problem using Gauss's law. So basically the same kind of thing. I'll give you some sort of configuration and then ask you what is the magnetic field at different locations in that configuration. And then from there, ask you to plot it and do all that kind of good stuff. So basically the same idea as what we did for Gauss's law. Now, the only thing difference between Ampere's law and Gauss's law is Gauss's law had multiple configurations. There could have been spherical and there could have been cylindrical. When it comes to Ampere's law, there's one. Cylindrical. That's basically it. Okay, so life is great. Now, the only thing here is what's going to happen is you'll have different densities, right? Different current densities, which may or may not be constant. So if it's constant, all that means is that I enclosed here is going to be equal to J times the area enclosed. If it's not, you'll just have to do a simple integral over it, and then life will be great. So since everything is going to have cylindrical symmetry, what that means is the left-hand side is always going to be just B times 2 pi r. So left-hand side will just be that. Nice and easy. So good, so this is a long problem. So again, one long problem will be Ampere's law. Another one will be Gauss's law, or not Gauss's law, sorry. Analog of that. Sorry, Faraday's law, basically mixed with some other stuff like forces on wires and all that kind of good stuff. Also remember your powers lost, your power by an external force, all that different stuff when it comes to Faraday's law. So we did those in those example problems that we looked at. So just look at those. And then the last one is, right, so magnetic force on charged particles using a lot of different right-hand rules and a lot of those equations that I wrote down there. So, right. Let's talk about short problems. So, short problems will involve, one other thing I should say is the velocity selector. This will also be part of long problem number 1. So make sure you know about velocity selectors. Good, so let's talk about short problems. So short problems will be this stuff. So this will definitely be a short problem. So short problem 1 is going to be wire, loop of wire and an external magnetic field. So look at torques and potential energies and work and all that kind of different stuff. So that's one long problem. Conveniently, a second long problem is right above that. Hall effect. So look at a couple of those example problems we did for Hall effects, kind of see what type of questions that might come up. And then finally, the last one will be force between parallel wires. If you noticed, I never said anything about Faradays law. This one won't be out there. Drew that pretty picture for no reason. Everything's okay? So, that's about it. Any questions on the exam? Yes, Zach. Sure, I would love to. Let's talk about right-hand rules. Good. So we have, in general, 3 right-hand rules. So let's talk about each right-hand rule. So right-hand rule number 1 is good for one thing and one thing only. And that is the B field of a wire. So what this one says is, step number one, we would then point our thumb in direction of current. Step number two, our fingers curl in direction of the B field. So all that means is if here was, say, a wire, and I have currents running through it in this direction, so what we do here is we put our thumb in the direction of the current, our fingers would then curl around in the direction of the magnetic field, which means our magnetic field in this case would be doing that. So that's right hand rule number one. Okay? That's it. That's all that one is good for. So let's look at right hand rule number two. Right hand rule number two is anything with a cross product, which are a lot of things. So I'm going to write my cross product in general as A cross B is equal to C. So the way this one works is step number one, point fingers toward A. Two, curl fingers, smallest theta, toward B. Three, thumb, direction of C. So anything involving a cross product satisfies this. So three off the top of my head that go with cross products are F equals to IL cross B. So it works for this one. In this one, A is L, B is B, and C is F. This also works for F is equal to QV cross B. And then also for the torque, which is equal to mu cross B. So these are all the ones that this one works for. Now, the only caveat here is this one. So this one, if the charge is less than 0, then step number 4 is rotate by 180 degrees for C. Okay. So basically all it means is if you had your velocity is this way, your magnetic field is this way, you would have your thumb pointing in this direction. So that would be the direction of the force. But if it's a negative charge, that means I have to rotate by an extra 180 degrees to make the force in the opposite direction. So that's the only caveat to all this, is the charge is negative. So again, all this means is, so let's do a couple of examples. So if my velocity is this way, let's say my magnetic field is coming out in this direction. So again, here I point my fingers in the direction of the velocity, curl towards the magnetic field in the direction of the smallest angle, which means I got to rotate this way, curl, which means my thumb then points down in this direction. So this then would be the direction of the magnetic force. Okay. Another example. Let's do another example. I don't know. Let's say the current is coming out, and I don't know. Let's say the magnetic field is this way. So in this case, again, fingers go in the direction of the current, which is this way. Magnetic field is up, so I got to rotate my palm upward, curl towards there. My thumb points in the direction of the force. So in this case, my force would be pointing in this direction. Just a couple examples. It's okay. Right hand rule number 3. So right hand rule number 3 satisfies actually many different things. So this is actually for the direction of the magnetic moment or the area. And this is also for the direction of the induced magnetic field from Faraday's Law. There's something else that satisfies too, but I'm drawing a blank. Anyway, we'll talk about this. So the way that this one works is step number 1, curl fingers in direction of I to thumb points in direction of mu, or the area, or the induced magnetic field. All of these are the same. Now, the caveat here, though, is that typically when we do Faraday's law, i.e. the induced magnetic field, we actually have to do this backwards, because we know the direction of the induced magnetic field, which means we would actually start off by putting our thumb in the direction of the induced magnetic field, and then go to step 1 to put our fingers in the direction of the current. So typically the way it's going to work is when I'm dealing with Faraday's law, I'm going to know this first. So I'm going to start off with this and then go backwards to this one. So let's talk about this one. Let's do for the area slash the magnetic moment. So let's say here, if I had a loop of wire here with a current, let's say going in this direction. Bless you. So in this case, I would curl my fingers around in the direction of the currents, which is going this way. So my thumb points in the direction of the magnetic moment. So in this case, my thumb is pointing into the board. So this would be the direction of the magnetic moment, hence the area. If I had an induced EMF problem, so let's say I had a motional EMF problem. In this case, let's say I have a rod, which is moving in this direction with a velocity of v, and I have an external magnetic field. Richie, what direction do you want your external magnetic field to go? Into the board or out of the board? Out of the board, great. So this is my direction of the external magnetic field. In this case, since this rod is moving this way, then the effective area here, which is this area, is increasing, which means the flux is increasing. So since the flux is increasing, does Lenz's law tell me I have to make a magnetic field in the opposite direction or the same direction? If the flux is increasing. Is it same direction or opposite direction? Opposite direction. So that means I have to induce my magnetic field into the board. So in this case, I get a B field into the board. This is my induced magnetic field. So in this case, I would then point my thumb in the direction of the induced, curl my fingers in the direction of the current, which means in this case, my current would be going in the clockwise direction. So this is I induced. Okay. So when it comes to Faraday's law, we start off with this, understanding what's happening here, and then go backwards. So we actually do step 2 first, and then do step 1. But that's it. So these are your 3 different right-hand rules. So right-hand rule number 1, again, is only for the magnetic field of a straight wire. That's it. Or any curved wire, doesn't matter if it's straight or curved or whatever. Right-hand rule number 2, anything with a cross product, that gives us that direction. Right-hand rule number 3 deals with magnetic moments and induced magnetic fields from EMFs. I want to say there's something else involved in there too, but I can't. I'm drawing a blank. Getting too old to remember things. Okay. So, any other questions? That was a great question. This is okay. Any questions on anything? What's the bonus? What's the bonus? Good question. Another great question. The bonus deals with self-inductance. Any other questions? Okay. Good. So, let's bring up your final group assignments. How many group assignments do we have right now? You think it's what? I think it's like 10 points for the group assignments. I'm nice. Okay. So this says we have in a region, circular region, there is a uniform magnetic field pointing into the board. An XY coordinate system has its origin at the center of this circular region. A free positive charge of charge 1 microcoulomb is initially at rest at the position x is equal to 10 centimeters along the x-axis. So if the magnitude of the magnetic field is now decreasing at a rate of -0.1 teslas per second, what force, magnitude and direction, will act on the charged particle? So let's draw the picture. Okay, so here is my XY coordinate system. So X and Y. So what this says is I have a circular region of external magnetic field. So it's doing this. It's my circular region. And what direction did it say it was going? Out of the page or into the page? Pointing. All right, okay. Into the page. There we go. Good. All right. So this guy's pointing into the page. So what I know here is I have magnetic field pointing into the page. Good. And now what it says is that I have a charged particle which is sitting here at a distance of x away from the origin along the x-axis, where x in this case is equal to 10 centimeters. Okay. So what I'm going to do then is I'm going to cause this magnetic field to decrease at a rate of dB dt equal to, what is it, 0.1 teslas per second. Right? And the negative sign just means it's decreasing. So let's go right in as a magnitude for now. So for there, I want to know what is the force, magnitude and direction on this guy. So this has to do with the actual version of Faraday's law. So we know that we have the closed loop integral of E dot dl is then equal to minus the number of loops, which in this case there is 1, times then the time rate of change of the magnetic flux. So basically what's going to happen is, since the magnetic flux is decreasing over time, what I have to do then is induce a magnetic field into the board, because the flux is getting smaller, so my induced magnetic field is going to be in the same direction, which means I'm going to create circular loops of electric field, which in this case, I would point my thumb in a direction, my current would go around in this direction, but the current is in the same direction as the electric field. So in this case, I'm going to create circular loops of electric field, which are going to do this. This is my electric field. Which basically means that what? At the point of the charge, I'm going to create an electric field then, which points downward at this stage, right? It's okay? So remember, going way back to the second exam, that the force on a charged particle by the electric field is equal to the charge of the charged particle times the electric field. So basically, all you have to do then is use this to find the magnitude of the electric field. From that magnitude of the electric field, you multiply simply by that charge that I told you, and then that's the magnitude of the force. The direction then is going to be either downward in the negative y direction or upward in the positive y direction, depending if the sign of the charge is positive or negative. Was it a positive charge or a negative charge? I don't know. It was a positive charge, so the direction of the force then is going to be in the negative y direction. So ultimately, this thing is generating an electric field. That electric field is going to put a force onto that particle. So you need to find out what is the electric field magnitude at the distance of 10 centimeters away from the origin. So in this case, the radius is 10 centimeters. So it just means that for this electric field, oops, a little bit bigger, electric field that goes through here, this is at a radius of 10 centimeters. Okay. So that's it. So that's the last one. So not too bad. Not too bad. Again, since this is a circle, DL will be in the same direction as that, which means the left-hand side is simply going to be E times 2 pi r. And then that's going to be equal to, here the area is constant as far as the magnetic field is concerned, so this is then just equal to time rate of change of B times A. I'll let you guys fill in the rest of the blanks. So not too bad. So there's only like 6 minutes left, so I'll let you guys start working on this, talk about those. So tomorrow we'll have the exam. Monday should start new stuff, but we're going to finish off this chapter just because I feel like it. So we'll start putting inductors into circuits. So we'll look at 3 different circuits. We're going to look at LC circuits, RL circuits, and RLC circuits. Okay, so we're going to look at the 3 of them, talk about the difference between those, and then on Wednesday we'll start the last stuff for the remaining of the semester. So for that, the nice thing about the next test is there's one hard part. That'll be at the very beginning. And then after that, the rest is just optics, which is nice and easy. So basically, optics is based off of 2 equations. Life is great. So nice. So last exam is usually pretty easy. Okay. So like I said, I'll let you work on those, and I'll give this to Molly. Sure. So it depends on the direction and what he is doing, or at least what the flux is. So in this case, we're told that the magnetic field runs inward, but it's getting smaller over time. So since it's getting smaller over time, I have to reduce the magnetic field in the same direction to counteract the fact that it's getting smaller. So remember, what the induced magnetic field wants to do is cause the system to try to remain as constant as possible. So that means if this magnetic field is actually getting bigger, it doesn't want it to get bigger, wants it to stay the same, so it would be in the opposite direction. So I have to always think about the 2 things. What's the direction of the field? And is the flux increasing or decreasing? Okay, the flux can increase and decrease multiple ways. So either the field itself can be changing, or something else is changing, like the area. So it is like the motional EMF ones that we were looking at, when the area starts out like this and then it gets bigger. Well, in that case, the flux is getting bigger. So there's multiple different ways that the flux can change. So I just have to pay attention to what's the flux doing and what's the direction of the flow. So if the flux is increasing, that means my induced EMF has to be in the opposite direction. But if it's getting smaller, it has to be in the same direction. So it always does the opposite. Oh, that's only dependent on what's going on. So the one that we did, and I think we had 2 wires. One was here, one was here. But I was trying to levitate this one so it didn't fall under the EMF. So basically, what I did was the gravity was trying to push down, so I had to create a magnetic force up. And a traffic force to maintain a So that's where the gravity came into it. That's where Mars came in. So in that case, I just said, well, the magnetic force had to equal the gravitational force. And then that's where. But in general, that doesn't have anything to do with this. Okay, so Mark. Yeah. Hopefully. What's up?
No, I had this question before. She asked me a question.
I did see her hand. It's like,
I refuse to do it, man. I'm just like, man.
because in this case, there would be 0
I don't want
flux.
to do it. I just read because my class.
Because the area would be perpendicular to the direction of the magnetic field, so the flux would be 0. So it would just fall.
To get ahead of this class.
Well, yeah.
And then it's like 8 o'clock back.
And the acceleration would always just be.
And then I want to like do other stuff.
Yeah. Okay, what's going on?
Okay, so this is just the same thing as
Yep. So what A do we care about?
that's one. So
Right, so we only care about the flux through the circle of interest. So the circle of interest in this case is only the radius of the so it's just going to be the same R as that. So yeah, so it's just higher. It's always that. So I only care about the flux through the loop at which I'm like have.
because your radius is the same.
Well, no, that's not coincidence because that's what I want. Because I know the particle is directly at 10.
Okay, so it's just going to work out for cancel off. Well, at least one of them.
Because I have an R squared with a
Yeah.
Get the chart.
Right, divided by 2.
That's it.
Should we just take that?
That's right.
And then.
Why was it 5?
Oh, that's right, it's not that crux.
Yes. Pretty good.
But then for the, so then, so I just, so then we would just use 10.1 times this times 1.5 divided by that.
Divided by 2. So what are those 0.1 ones? What's that? Yeah, it was on the slide. I'm thinking about
A small number. Because you have to do your marker. That's what I'm saying. I'm getting like
let's see here.
Because you're taking, yeah, you're taking the times.
I just want to make sure that you're taking
So yeah, so the slide says it should be 5 nanonewtons in the negative J direction. What that? Nice. Very nice. I said, it seems scary at first, but it's not too bad.